Hi again everyone, Chris Tisdell here again. In this presentation I'm going to continue my series of videos on complex numbers, and in particular I'm going to show you how to factor complex polynomials. So let me share my screen with you and we'll get started. Alright, so before we get down to do an example, let's just summarize the basic theory for complex polynomials of degree n. So suppose I have a polynomial, and here the coefficients, the an's, the a sub n minus 1s, the a1s, etc., could be complex numbers. So for example, you might have a complex polynomial looking like this: iz squared plus z plus 2i, or something like that. Okay. All right, there's 4 main points here. Let's go through them one by one, and then we'll do an example. Every polynomial p of z of degree n has at least one root in the set of complex numbers. That is, there is at least one number alpha such that p of alpha equals 0. That's what we mean when we say alpha is a root of a polynomial. P of alpha equals 0. Okay. Now, if the coefficients are all real, so the a, n's, etc. are all real, then the roots of complex numbers appear in conjugate pairs. And we've seen examples of this in previous videos where I solved certain polynomial type equations with real coefficients. Now there's a factor theorem as well. If alpha is a root of the polynomial p, then z minus a is a factor of p of z. So this is like an extension of the factor theorem that you see at school. Okay. Let me just turn my volume up a bit. Okay. All right, well, the last one. Every polynomial of degree n can be factored into n linear parts. That is, I can write my polynomial as the product of z minus each of the roots. Now, the a sub n out here is the coefficient of the leading term, if you like. Okay. All right, so there are 4 important points. I'm not going to prove them, but I'll show you how to apply the ideas via an example. Okay, so let's talk about the following example. Here we've got a polynomial, p of z, defined to be z to the 6 plus 64. Okay, so the polynomial's there. It is a polynomial of degree 6, and the coefficients are all real. So we know that the roots of this polynomial will appear in conjugate pairs. And lastly, the second thing we're asked to do there is to factorize p into linear parts. Okay, so we want to find the roots essentially and write them like this. Okay, all right, so how do we do that? Well, let's solve this equation for z. Find the zeros or the roots of the polynomial. Okay, once we know that, the factor theorem says that we can write p of z like this. Okay, so we have done other questions like the first part, so let's just refresh our memory. For this type of problem, we will convert to polar exponential form. Okay, so we have the following. Z to the 6 equals negative 64. Let me just adjust the focus on this. Okay, so we write the right-hand side in polar exponential form. Okay, so if I plot negative 64 in the complex plane, it's going to lie over here somewhere. Okay, just a real number. Okay, now, so I go out 64, I go around half a revolution, and I go out, say, 64 units. Now, if I want to write that in terms of the polar exponential form, then I can do it the following. You have a length, 64 units, from that point to the origin, and you've gone around half a revolution. That's pi radians. Okay? Now this can be further, the first part can be written as 2 to the 6th, and we have a 6 there, so that's going to simplify. But also, the polar form is not unique. You can keep spinning around more and more revolutions to get back to the same point. So to make sure we catch all the solutions to our problem, we can introduce a 2k pi in here. That gives us all the possible ways of getting to that point. Okay, all right, so now we've got this, what we can do is take the power 6 to the other side and try to simplify. Okay, so if I take, if I take power 6 of both sides, well, that will disappear, and I'll divide this exponent by 6. Okay, and this is, again, true for k equals 0, plus or minus 1, plus or minus 2, etc. Okay, so here then is like a sequence of solutions to our problem. Okay, now some of these values of k are going to give identical solutions. All right, so what we're going to do, we're going to start with the simplest value of k and just write out 6 solutions to our problem. Okay, so let's start with k equals 0 in here. So by the subscript, I'm taking the value k equals 0. So that'll disappear. I'll get 2e to the pi I over 6. So that's one solution. Okay, let's take another simple value of k. K equals 1. Okay, that'll give me 2e to the pi. I'll get 3 in there, and then I over 6. So that'll reduce down to the following. All right, let's keep on going. Let's put in, say, k equals positive 2. So I'll get, again, something like this, and I'll get 5 in there. Okay, now let's choose another simple value of k, say k equals negative 1. So I'm going to get negative 1 in here. Okay, let's try k equals negative 2. Okay, so up here I'm going to get negative 3 in there. So that'll simplify down to the following. And lastly, k equals negative 3. Okay, so now I have 6 solutions. I can stop. If I kept going with other values of k, I would keep getting back to one of these solutions. Okay, so here are the 6 solutions to my problem. Okay, so notice that they do appear in conjugate pairs, just like we had hoped them to appear. Okay, from this part here. And I know from the factor theorem I can write this, the p of z, as z minus that times z minus that times z minus that, etc. Okay, now I can simplify a little bit more in here. E to the pi I on 2, where you go around a quarter of a revolution and out 2 units. That's lying on the imaginary axis, so that is just 2i. And same here, you go the other way, a quarter of a revolution, so that would be negative 2i. Okay, so now I can write the following. It's just the following here. Z minus this times z minus that times z minus 2i times z plus 2i times z minus that times z minus that. Okay, so it's a bit of a mess, but we got there. Okay, now if you were to plot these in the complex plane, that they would lie on a circle centered at the origin with radius 1. So let me just sort of give a real basic freehand drawing here. Okay. All right, so you've got one there, one there, one there, one there, and one there. Okay, so those points are your roots. Okay, so a very rough sketch there. Okay, so that's it, just applying the factor theorem, finding the roots, etc., etc. So that's a reasonably interesting application of some of these properties here. Okay, so that's my example. Hope you enjoyed it. In forthcoming videos, I'll be doing some more examples like this, which are pretty involved. If you have any comments, any questions, you can always post them in the comment section below. Hope you're enjoying these series on complex numbers. Join me for forthcoming presentations. See you later. Bye.